Bayesian linear regression. In the last lecture, we'd seen what are the differences between frequentist approach to linear regression and Bayesian approach to linear regression. In this lecture, what we are going to see is what is Bayesian linear regression and how can you make the estimation of probability distributions using the Bayesian linear regression. So before we do this complete detailing of Bayesian linear regression, let us have a slight recap of what we learned in case of frequentist or the classical approach. Because once you have a slight recap of that, you will be able to clearly identify what is the difference in Bayesian and how different these two approaches are. So in case of frequentist, this is what you did. You had an equation like yi is equal to w0 plus w1xi plus epsilon. So this epsilon term, I'm considering this as an error term. That is, you can consider it as noise or the irreducible error. So you won't be able to make exact estimation of yi using w0 plus w1xi. There will be a slight error that I'm considering as epsilon. Okay. So this was the equation that you had in case of frequentist linear regression. And how did you find the values of w0 and w1 there? You didn't have the concept of probability distribution at all. You were making point estimates of w0 and w1. And how did you make it? First you said there is an error term. What is error? Error is the difference between the observed value and the predicted value. So I'll call this y cap to say that this is the predicted value. You have observed value x and y. So this y minus the predicted y, that is what error is. So error was, let's say, yi cap minus yi the whole square. This you did for all the data points. Sigma I is equal to 1 to n. And what did you do? You tried to minimize this error and you found out what is the value of w0 and w1. That is the optimal values of w0 and w1 that will keep the error term to the minimum. That is what you tried to find out in case of frequentist approach. So you try to minimize the error and find a directly optimal value of w0 and w1. Let us see what is the difference in Bayesian approach. How do we approach in order to find w0 and w1 in Bayesian? So this is a totally different approach. First thing is you don't have any point estimates here. You consider everything as probability distributions. So you are going to find the probability distribution. You want to find the distribution of w0 and let's say some distribution of w1. And from this you are going to take the values. So let's start. In Bayesian you have the same equation. Y is equal to w0 plus w1x plus epsilon. The same equation you have. But the way you find w0 and w1 is totally different. You have a prior belief, then you will update this prior belief with the data. So data means here it is the likelihood. Using the likelihood, you will update the prior beliefs and you will find the posterior. And posterior is what is your final distribution for w0 and w1. So let us say you have a prior belief about w0 and w1. My prior belief is P of w0. Let us say w0, it has a normal distribution. Normal distribution, that is a Gaussian distribution with let's say mean of 0 and variance I'll say I'll keep as tau 0. Okay, tau 0 square, this is the variance. So you normally take mean as mu and variance as sigma square. So this mean is 0 here and sigma square, the variance is tau 0 square. Why am I using tau 0? Because I want to use sigma in likelihood. So in order to differentiate, I'm using tau 0 here. And let us say my prior belief about w1 is that the probability distribution of w1 is a normal distribution with mean of 0 and variance of tau 1 square. So how will this distribution look like? We already learned about normal distribution. And how do you write the equation of normal distribution? It is like this: 1 by root of 2 pi tau 0 square e raised to minus of, we said x minus mu the whole square by 2 sigma square. So here what is x minus mu the whole square? In place of x, you will have w0, your mu is 0. So it is minus of w0 square divided by 2 sigma square. So in place of sigma, it is tau 0 here. So 2 tau 0 square. So this is your equation for probability of W0. This is your prior belief. That is, even before you see the data, this is the prior belief you have about W0. So you already said, I have a prior belief that this is my normal distribution of W0 and it is represented by this equation. Okay. Similarly, for W1 also you have a prior belief. It's a normal distribution with mean 0 and variance of tau 1 square. So the equation would look like this: 1 by root of 2 pi tau 1 square e raised to minus of w1 square divided by 2 times tau 1 square. Okay. So this is how my equation for W1 would look like. So this is my prior belief about the W0 and W1. So what I'm going to do is, I have a prior belief about W1. Similarly, I have a prior belief about W0. I'm going to update this belief as I see the data. So as I see the data, I'll update this prior to posterior, and posterior is my final distribution. So let us see how do we update. So this is what we have as prior. Next thing is data. In case of frequentist, data was considered as the exact values that you were provided. In case of the Bayesian approach, you don't have any concept of exact point estimations. Instead, everything is probability distribution. Whatever value you are considering, you should consider as probability distribution, and from this distribution you should try to find out the value. So you already have a distribution for W0, you already have a distribution for W1. What is the next thing? You need the distribution of your data. You see the distribution of data, you see the distribution of prior, you use both of this information, that is the prior distribution and the distribution of data, and you find out the posterior. This is the concept. So let me write likelihood here. So by likelihood we express data. Okay, so this is my likelihood function. Likelihood function would look like probability of what will be present in data. Data will have x and y values. This is what your data would normally have, right? In generally, you'll be provided with data which is a set of x and y values. Using this data in frequentist, you directly found out W0 and W1. In case of Bayesian, you have a prior now. Now you're going to introduce this data to that prior and you're going to find posterior. So how do you see data? Data you have to see as probability distribution of data. That is probability of y given what are given, x is given, then W0 is given, W1 is given. This is your assumption. Given x, W0 and W1, how will the distribution of y look like? If you know this, you have data, right? So you have x and y values. You're going to express it as probability distribution. So how will you express it as a probability distribution? So before we take complete y, let us take one particular value, that is xi, yi. There are n data points. Let us just take one data point and see how we form the probability distribution for that one particular data point. I am taking yi, xi. In that case, what will be my probability distribution? It will be a normal distribution with what will be the mean? I already have xi and yi. So my mean will be W0 plus W1 xi, right? This will be my mean. And what will be my variance? I'll consider variance as sigma square. Okay. So this is my distribution for likelihood. This is my likelihood function. So I'm going to write the exact likelihood function, which will consider all the n data points. Considering that, it will be probability of y given x, W0 and W1. Okay. This would be you have n different probability distributions which are normal distributions. What will you do? You will take the product of all those distributions, that is pi I is equal to 1 to n. Pi denotes product of all the distributions. N means normal distribution with a mean of w0 plus w1xi, and what is the variance? It is sigma square. So this is how I represent the likelihood function. Likelihood is how my data is represented. I don't simply provide data as xi, yi. Instead, in the Bayesian approach, the data is provided as the likelihood, probability of y given x, w0 and w1. So if you want to write the equation, you can just write the equation of a Gaussian distribution with mean of w0 plus w1 xi and variance of sigma square. How would that equation look like? It would look something like this: 1 by root of, what is the variance? Sigma square, root of 2 pi sigma square e raised to minus of it should be in x minus mu. What is the equation? It is 1 by root of 2 pi sigma square e raised to minus of x minus mu the whole square by 2 sigma square. So what is x here? It is yi. Okay, yi minus mu is mean. What is mean here? w0 plus w1 xi. So you have to write w0 plus w1 xi the whole square divided by 2 sigma square. So this is your normal distribution, the equation for your normal distribution. So this represents the normal distribution or the likelihood function. So at this point, what all things do you have? You have a prior belief, you have prior, which is P of W0 and P of W1. Then you have a likelihood. What is your likelihood? Likelihood is this one, your belief about the data, complete data you have of n data points, and that belief is what you call as likelihood, probability of y given x, w0 and w1. And what does the Bayes theorem say? According to the Bayes theorem, your posterior is directly proportional to likelihood into prior, right? This is what your Bayes theorem says. If you take a multiplication of likelihood and prior, you will get posterior. Your posterior should be directly proportional to this. So you already know the prior. You have probability of W0 and probability of W1. That is your prior belief, which we already took. Then you have the likelihood that you have here. If you take a product of likelihood and prior, according to the Bayes theorem, you will get a value that is proportional to your posterior. So how do you find posterior here? This is how. Your posterior is probability of W0 and W1 given y and x. That is what posterior is. That is after seeing the data, after observing the data, what is the probability distribution of W0 and W1? This is what you call as posterior. What is prior? Before seeing the data, what is the probability distribution you're assuming for W0 and W1? Likelihood is in effect data. That is, you're giving the distribution of data, you're giving your prior belief, and you are asking it what is the posterior. That is, what is the probability distribution of W0 and W1 after you had seen the data. So that is probability of, I'll write again, probability of W0 and W1 given y and x. This is what your posterior is. This should be directly proportional to what? Likelihood into prior. What is your likelihood? It is the probability of y given x, w0 and w1. This is your w0 and w1. This is your likelihood. Likelihood into prior. What is the prior? You have P of W0 and P of W1 as prior. So into P of W0 into P of W1. This is what your posterior is. If you want to take posterior, you have to find the likelihood. You should have the prior of W0. You should have the prior of W1. Then if you multiply likelihood by the prior of W0 and the prior of W1, then you will get a value which is proportional to your posterior distribution. And how do you find the exact value of posterior distribution? That is, in order to find any distribution, any normal distribution, you need mean and variance. If you know the mean, if you know the variance, then you know exactly what the distribution is. You can plot the distribution, you can clearly understand what the distribution is. So in order to find any distribution, you need two values. One is mean and the other is variance. So when I say probability of something, in order to clearly estimate this distribution, two values are what you have to find: the value of mean and value of variance. So how do you find the exact value of mean and variance of this posterior distribution? This is what it all boils down to. In case of Bayesian linear regression, what you finally have to do is find the mean and variance of this posterior distribution. If you know the mean and variance, you are done. You have the posterior distribution of W0 and W1. How do you find that exact estimate? This parameter estimation, that is finding mean and variance, this is estimated using some techniques like Markov chain Monte Carlo or variational inference. So you have these techniques. So when we learn those techniques, after we learn those techniques, we'll come back to this and see how you can derive this. For now, you just understand there is something called MCMC, that is Markov chain Monte Carlo, or you can use variational inference. Using this, you can make exact estimation of mean and variance of this posterior. Once you find the mean and variance, you know the distribution. That is it. Okay. And so in nutshell, this is what you have to understand, that in case of Bayesian linear regression, it incorporates prior beliefs about the model parameters, that is P of W0 and W1, updates these beliefs using the observed data, that is your likelihood. This is how you took your observed data. Using the observed data, you updated your prior belief and you used Bayes' theorem for this, and then it provides a posterior distribution. This is the posterior distribution. So this posterior distribution, it quantifies the parameter uncertainty and it supports probabilistic predictions. So this is what you do in case of Bayesian linear regression. If you are having this doubt as well, that okay, I found W0 and W1. Once I find the exact values of W0 and W1, exact value in the sense not point estimate, distribution, probability distribution of W0 and W1. Once you find it, how can you actually see what is the value of Y using this? So that you can find out from the equation for Y that we wrote, W0 plus W1 xi. Or if you have to calculate it, you can, that is, if you want to calculate the distribution, then you can calculate the probabilistic distribution. How can you do that? You can do something like this. That is, you have probability of, let's say there is a Y new that you have to calculate based on some X new. You have a new value of X. So I'm saying X new, and you have the data, that is Y and X, which is the previous data. You have an X new and Y and X, which are the previous data. What would you do? You would integrate between all the values, then probability of Y new given X new, and what are the other given things? One is your parameter W0 and one is W1. X new, W0, W1. And you will take probability of W0 and W1 given the values of Y and X. So W0, W1 given Y and X into dW0, dW1. So if you do this, you will get the probability distribution of Y new. So this is how you can finally estimate exact ones for Y new. So for now, just understand this thing, that you have to find a posterior. Posterior is to be found from likelihood and prior. That is good enough for now.